Good. All right. Well, there's the word. So we're asking if the third column. This column is like. So this is the third column. So it's linear combination. It is right out. So can you express this linear combination? That's all we're asking. Find C1, C2, C3. Yeah, based on what I do. Just look at it. Right, third column, linear combination of column. Not hard. Just write out what you're asking. Okay, great. So let's see, let's do the desktop. Okay, that's, all right. Okay, we're all set up. Gone. Including myself. so this is the second. Okay, great. All right, let's do a sound check. Can people hear me on the other end?
Yep.
Yeah.
Yes? Okay, we can hear you, great. Okay. Okay, so first announcement, so the homework is actually due today. So I'd appreciate if you can upload your homework onto your OneNote folders. And then we'll start to process the homework this week. Hopefully we can get it back to you by next week. Okay. And if you have not received a folder invitation, please send me an email. We had a couple of instances where we actually had to rectify this problem, and we were actually able to do it. So if you have not received a folder invitation for the OneNote, again, please contact me. So the notes for the class are pretty much up to date on ELC. So if you want to download the notes, the course notes that I'm actually writing out, they're available up until the last lecture. And I'll continue to do this on ELC. And I've actually downloaded all the videos from Zoom on my computer. So this weekend, I'm actually going to work on setting up a YouTube channel so that the videos from the class will be available. So hopefully we'll have some success by next week, and you'll have those resources available. Okay, any questions?
Professor, real quick, you're a little bit quiet for us over on Zoom.
Okay, let's see. I wonder if I have to stand a little closer. Can you hear me better now?
A little bit, but the mic quality in general is a little bit lower than it used to be.
Let me see if I can fix that here. Audio. Okay, so let me increase this. Can you hear me better now?
Yeah.
Yes? How about
Yes.
that? Okay, great. Yeah, I just increased the mic volume. Okay, good. Okay, hang on a minute. Okay, great. Okay, so we can actually begin now. And so let me just back up a little bit and recall some of the ideas that we had from last class. So we were talking about systems of equations. So in general, if we have AX equals B, yes, where B is not zero, this is what's called the non-homogeneous system. Of equations. All right, so if you have a B which is not zero and you're looking at a system AX equals B, then that's a non-homogeneous system of equations. Now, in the case when B is actually equal to zero, the zero vector, this is called the homogeneous system. Okay. And last time what we showed was these systems of equations are actually interconnected. So if you want to know the solution for the non-homogeneous system, you only actually need to know one solution. And once you have one solution, you can add it to any homogeneous solution and then you can get this, all the solutions for the non-homogeneous case. So let me actually write this out. So this was part of this theorem. Okay, so let A be an m by n matrix, okay, and consider the system of equations AX equals B. Okay. So let X of P be a particular solution of AX equals B. So, just pick one. Pick any one you want. Okay? So then, the set of solutions for AX equals B are of the form X, where X is the particular solution plus a homogeneous solution. So this is where, whoops, get rid of this there. Okay, so where X of H is in what we call the null space of A, which is the set of all solutions of the homogeneous system. Okay, any questions on the statement of this? All right, so again, let me draw you a picture of what's happening. So here's the picture, let's say we have free space here. Right? And as I've drawn before, let me just use different colors. That seems to work out well. So down here I have my, oops. So down here I have my null space. So this is the null space of A, which are the homogeneous solutions. Okay. Now, in order to get the general solution for AX equals B, I take a particular solution, and then what I do is I sort of lift the plane up to that particular solution. Okay, so let's do that. Oops. And let's change color. And let's take a particular solution. Call it X of P up here. And then to get all the solutions, what we can do is we can just shift the plane up to that point up here. So these planes are parallel, and this represents the solutions of AX equals B. Just clean it up a little bit. Oops. Try it again. Let's try to draw it in just a little bit nicer. Perfect. All right. Does that make sense? Yeah, go ahead. No, it's just a plane still.
So like the base plane.
So the blue plane represents the homogeneous solution. The green plane represents the solutions of AX equals B. all the solutions are on the green line. Okay? So the thing is, all you're doing is you're taking the homogeneous solutions and you're shifting it up by a particular solution. One particular solution. That's all you need. Okay?
I have a question real quick.
Go ahead.
Do all matrices like A have a null space?
Yes. Good question. So you know that it's not empty, right? Because the zero vector is in the null space. And what we'll do later is we'll actually show that it's going to be a linear space. It'll look like a plane or, you know, 3 space. And we'll actually find what's called a basis for the null space later on.
Okay, thank
Good
you.
question. Okay. We'll study it more in depth. Okay, other questions?
Yeah, I have a question.
Yeah, go ahead.
So the null space of A, that can be either a point or a line or a plane or however many dimensions there are.
That's correct.
Okay, that's all.
Okay, it's going to be equal to, well, let's see. It's going to be equal to the number of free variables. So we'll do an example in a second.
Okay, thanks.
Okay, these are all good questions. All right, so let's apply this to a particular example. Now, we did a really easy example last time, so we'll do a more sophisticated example this time. All right. Okay. So here's the example. Oops. Let me change colors again. So here's our example. Okay. So solve the system of equations. Okay, so let me give you a particular one. So we have x1 plus 2x2 minus 7x3 is equal to 0. Minus 2x1 minus 3x2 plus 9x3 is equal to 4. And then finally, minus 2x2 plus 10x3 is equal to minus 8. Okay. So this is a 3 by 3 system of equations. All right. So, you know, we should be thinking about this as, you know, a system like AX equals B. All right, so first of all, how should we solve this system of equations?
Gaussian elimination.
Good. So let's use Gaussian elimination. So I'm going to put this in a matrix, and we're going to solve it. So 1, 2, minus 7, 0, minus 2, minus 3, 9, 4, 0, minus 2, and minus 8. Okay, does everyone see how we did this? Okay, we've done it a million times. Not quite a million times. By the end of the class, you'll have done it a million times. Okay, so now what we want to do is we want to just row reduce. So let's do that. So I'm just going to multiply that. I'm going to use the 1 as a pivot. And we just row reduce. So 1, 2, minus 7, 0. So 2 times the first row plus the second row, put the result in the second row. So what do we get with 0? What's next?
1.
1. What's next?
-5.
-5. Good. After that?
4.
4. Good. And then I just write the third row down. Okay. All right, so let's continue on. And so we have 1, 2, minus 7, 0. Multiply the second row by -2. Add it to the third row. but the result in the third row. If we still keep the second row the same, third row 0, 0. What's next?
20.
Minus
Nay 0. 0.
Okay. And the last one is a
0.
0. Okay. So first question. Is this system consistent?
Yes.
Okay. So are we going to have one solution, or are we going to have like infinitely many solutions?
1.
One or infinitely many?
1.
Infinitely many, right? So the point is that we have the pivots here. So the columns where the pivots don't occur are the free variables, right? So here's x3. So x3 equals t is a free variable. Okay, is everyone with me on this? And now what do we do?
We make like a parametric sort of vectorized equation with
So
t.
Yeah, so what's the term that we use in order to solve this system?
Back substitute.
Right, we back substitute. Okay. So then we use the equation like x2 minus 5x3 is 4. So x2 minus 5t is 4. So x2 is equal to 4 plus 5t. Okay, let me just box these things so that we keep track. Everybody okay so far? And now we just go up to the top equation. So we're just kind of moving our way up, right? So we have x1 plus 2x2 minus 7x3 equals 0. Okay, now let's substitute in x1 plus 2 times 4 plus 5t minus 7t is equal to 0. Okay? So that's x1 plus 8 plus 10t minus 7t equals 0. x1 plus 8 plus 3t, right? 0. Okay, so then x1 is equal to minus 8 minus 3t. Okay, everybody okay with that so far? All right, so let's write out the solution in general. So the solution is x1, x2, and x3. And that's equal to, we'll just plug it in, minus 8 minus 3t. Okay, x2 is 4 plus 5t, and x3 is t. And now what we'll do is we'll split out the vectors which involve the t and don't involve the t. So the things that don't involve t are minus 8, 4, and 0. Okay? Plus t times what vector? What vector do we have?
-3.
Okay? 5 and what? 1. Okay, so here t is a real number. All right, so question. So can anyone locate a particular solution for it?
The homogeneous solution is the t side of the equation.
Right, so the homogeneous one will be the t side. So let me just kind of circle that. So I guess we use blue, right? Is that the one for the bottom plane? So I want to coordinate this time. I don't know if I coordinated last time. So anyway, so this part here, this is the homogeneous solution. Okay, In fact, why don't we, I don't know if we can look this up. The disadvantage of this. Okay, I'll write it out again, okay? All right, hang on for a second. Okay, so then let me just circle the particular solution now. Oops. Okay, let's go with a particular solution here. And here. This is x of p, and this is a particular solution. X equals b. All right. Now, just to make sure that I'm not trying to pull a fast one on you guys, let's just check whether this is true. So, unfortunately, I don't want to scroll back and forth, so I had better rewrite the equations that we started out with. Okay, so it's very easy to check whether you have the right answer or not. So let me back up and put the equations down. So that's x1 plus 2x2 minus 7x3 is 0, minus 2x1 minus 3x2 plus 9x3 is equal to 4. And the last one is minus 2x2 plus 10x3 was equal to minus 8. Okay, so now I put the equations down. Now we can actually check whether we got the right answer or not. Okay? So let's look at the particular solution first. So when I plug in x1 equals minus 8, x2 equals 4, and x3 equal to 0, does it satisfy all three equations? Well, let's check the first equation. So I got minus 8 plus 2 times 4 plus 0. So that's 0. Everyone agree? Yes? Okay, so now let's plug in minus 8, 4, 0 to the second equation. So I get 16 minus 12 plus 0. Okay, so 16 minus 12 is 4, so everything's good there. And then finally, let's plug it into the third equation. So I get 16 plus 0. Oops, sorry, that's not right. It's minus 2 times 4 plus 0. That's minus 8. So everything's good. Okay, so we checked that x of p satisfies these equations. And now you can also check whether minus 350 is a solution for the homogeneous system. So let's do that. So I have minus 3 times plus 10 minus 7. Is that 0? Yes, right? So then I plug in minus 351 into the second equation. So I get 6 minus 15 plus 9. That's good? That's 0, right? And then finally, what's in the last equation? I get minus 10 plus 10. That's 0 also. Okay, so we check that this actually satisfies, the first thing satisfies the general equation, and then minus 351 and multiples of it actually satisfy the homogeneous. Okay, any questions on this? Yes? No? Okay. Good. I hope it's a very nice example. Oh, and then let me make one more remark. And so if I want to know about the null space of A, this is just the span of this vector here. Minus 3, 5, and 1. So the null space here is just one dimension. Okay. Good. All right, so now I'm going to start in on applications of linear systems. Yes. Okay, so let me just draw a line there. And we're going to talk about applications linear systems. Okay, so what I'm going to do is I'm going to do 3 examples. So the first example I'm going to show you involves balancing chemical equations. Okay, so we'll just work on this today. And then tomorrow or Friday, what we'll do is we'll look at networks. And then we'll probably look at some economic systems too. Okay. So what we'll do is we'll actually show that linear algebra can be used to solve problems involving things involving chemistry and like electrical engineering and also like economics too. So there's a wide applications to this theory. Okay, so what we're going to do first is we're going to look at balancing chemical equations. And so maybe, you've actually done this a different way before, but let me show you how to kind of look at this in a linear algebra type of context. All right, so the idea is the following. So you basically have 2 like compounds, right? And you actually mix them together. And when you actually mix them together, you get maybe some other compounds too. So, so let me start with this example. So you take a solution of what's called sodium phosphate. And what's called beryllium nitrate. Okay, so when you actually put these together, and here's the chemical symbol, so Na lower 3 PO4, I'll explain this in a moment, plus Ba NO3 2. Okay, so that's these compounds together. Okay? So what you get is beryllium phosphate, or sorry, barium phosphate, and sodium nitrate. Okay, so let me give you this compound here. It's called Ba3 PO4 2 plus Na NO3. Okay. All right. So when you put these 2 things together, your output get is this. So let me just do this by kind of indicating that the 2 together, you get this. All right. So what does it mean to balance a chemical equation? So what you want to do is you want to sort of take a certain number of atoms on the first compound, a certain number of atoms on the second compound, and then you want them to be equal to a certain number of atoms on the third compound plus a certain number of atoms on the fourth compound. So let me just say this mathematically. So to balance the equation, we want x1, x2, x3, and x4, okay, such that the following is true. So I have x1 times the first compound, Na3, PO4, okay, plus x2 times Ba, make sure I'm not dropping any subscripts, okay, that's very important. Okay, so I have a number of atoms. And the number of atoms isn't fractional, it's just gonna be some number, okay? And we want this to be equal to x3 times BA3 PO4 2 plus X4 times NA and NO3. Okay? And these things are integers too. So these are positive numbers. Okay, so the next thing I need to tell you is I need to tell you what these atoms are. So let's do that. So here are the atoms, the symbols. So the Na is the sodium. The P stands for phosphorus. O is oxygen. And N is nitrogen. And see, the Ba is barium. All right. Now, from this equation up here, so let me just put this in a box. So from this equation that I boxed up at the top, what we need to do is we need to actually write a system of equations which is reflective of the number of atoms. Okay? So in each of the columns of my vectors, that's going to represent the quantity of like sodium, phosphorus, oxygen, nitrogen, and barium. So let's do that. So I have X1 here. And I just need to put in certain numbers in the sort of first compound up here, which represent the number of atoms. Okay, so with sodium, because we have an Na3, we put a 3 down. Okay, so the first entry involves the number of sodium atoms. Okay, the number of P's is just 1. Okay? The number of oxygens is how much? 4. Okay. The number of nitrogens is how many? 0. Good. Numbers of barium. Anything? 0. Okay, does everyone get how we did this? All right, so you sort of make sure you line things up, and then those correspond to the coordinates of your vector. Okay, so let's move on. So I have X2. And this is going to be what? So how many NAs? 0, right? How many phosphoruses? 0. How many oxygens? Anyone?
6.
6, thank you. How many nitrogens? 2, good. How many bariums? 1, okay. And then you equate this on the other side like this, kind of neat. Okay, so we just go down the list again. How many NAs? Okay, how many phosphoruses? 2, thank you. How many oxygens? 8, good. How many nitrogens? Good. And how many bariums? 3. Okay, so you get the hang of it. I mean, once you, I mean, it's kind of rote, right? Once you actually have this and know how to do this, then you just be careful and make sure you just set it up correctly. Okay, X4. So how many sodiums? Very good. How many phosphoruses? Good. How many oxygens? Good. How many nitrogens? Good. And how many bariums? Good, great. Aha. So now we actually have something where we can actually solve for x1, x2, x3, and x4. So what we can do is we can set this up using a homogeneous system of equations. Okay? So let me just move it to the other side. And so we have x1. So I'm going to just do it in steps so that you can see that we do have a homogeneous system. Plus x2 times 0, 0, 6, 2, 1. Okay? And then I'm going to move the x3 to the other side, but then I have to negate everything, right? 0, minus 2, minus 8, 0, minus 3. Everyone agree with that? Plus x4, and I go to negate everything, minus 1, 0, minus 3, minus 1, 0. And that's equal to the 0 vector. Okay? All right, so this becomes a homogeneous system. So now I can just write it as a matrix here with 0, 0, 0, 0, 0, 5 zeros, and 3, 0, 0, minus 1, 1, 0, minus 2, 0, 4, 6, minus 8, minus 3, make sure I'm not making mistakes, 0, 2, 0, minus 1. Okay, it's not quite lined up as well as I wanted to. Sorry about that. 0, 1, minus 3, and 0. Okay, does everyone see that this is the system of equations that we get? It's a homogeneous system of equations. Everybody good with that? So now what do we do?
Gaussian elimination.
Okay, Gaussian elimination. Okay, so first thing we do is we want to get rid of this. We want to get rid of this 1. So let me just multiply the second row by minus 3, and then add row 2 to row 1 and replace it with row 2. So we have 3, 0, 0, minus 1, 0 here. We have a 0. So we have a 0 here, and then I have a 6. Yeah. And then I have a minus 1, and I have a 0. Everybody okay with that so far? Okay, so the next thing I want to do is I want to knock out this 4. So I can use the 1 here also to knock it out, right? So I can multiply this whole thing by minus 4 here, and then stick it in the second row. So I can do row 2 plus row 3 and put it in row 3. So let's do that. So this is going to be a 0. What's next? 6, right? And minus 4. So that's going to be a 0. Minus 4 times minus 2 plus 8. And I get a minus 3. And I get a 0. Okay? And let's just keep the rest the same. So 0, 2, 0, minus 1, 0, 0, 1, minus 3. Okay, so we're starting to reduce this matrix down. Okay, so good deal. So now I just want to switch. Let's see, what do we want to do? Why don't we divide? So you can also divide equations, right, by a non-zero number. So I can simplify this a little bit. So I can actually divide this one by 2. So divide by 2 here on the third row. Okay? So if I do that, 6 divided by 2 is what? 3, right? Oh, I'm sorry, I'm going to divide by 3. I'm sorry about that. So this should be a 2, right? And if I divide by this, I get a minus 1. Okay? And why don't we just shift it, change, and then I want to swap these two rows. Okay, that's allowed also. So I want to get the pivot, I want to get a pivot up in this part over here so that I can get in the upper triangular form. Okay, so let me just do that. Okay, let's keep the third row the same. 0, 0, minus 1, 0. Okay, so I'm going to shift row 3 up to row 2. So 0, 2, 0, minus 1, 0. And let's see. Do I want to do anything else? Okay, so I've got 2 rows like this. Let me just do it this way. Okay, I'm going to do it in several steps so that we don't get confused here. Okay, so let me just shift this one up first. Okay, so that's the 4th row, and then 0, 1, minus 3, 0, and then I'll put the last row 0, 0, 6, minus 1, 0. Okay, so I just changed the order of the rows in order to kind of make this in a nicer form. Okay, everyone all right with that so far? I mean, this is a bigger system than what we dealt with, so we have to actually have to kind of manipulate it more cautiously. Okay, so let's continue on. All right, so I want to eliminate this one over here. So again, let's multiply by minus 1. So I get 3, 0, 0, minus 1, 0, 0, 2, 0, minus 1, 0, 0, 0, 0, 0, 0. Okay, is that all right? And then for this next one, let's multiply this by minus 2, and then add it to the second row, and then put the result in the 4th row. Okay, so what do we got? We have 0, 0. Let's see, what else? 6, right? 0, minus 1, 0. And the last row, as you can see, works out to be the same thing. Okay, everyone all right so far? And now we can knock out the last row by using this row here at the end. Okay, so let's knock it out. Okay, so it's just a little game that we have to play here. So 0, 3, 0, 0, minus 1, 0, 0, 2, 0, minus 1, 0. Let's just keep the 3rd row as zeros for now. And then we have 0, 0, 6, minus 1, 0. And then finally we have the last row of zeros. So basically not for that. All right, everybody okay with this? Continue on. We're almost done. And we'll post this. So 3, 0, 0, minus 1, 0, 0, 2, 0, minus 1, 0. And then let's switch the row 6 minus 1 up. Okay. So 0, 0, 6, minus 1, 0, and the rest are all 0. Works out pretty nice. So if you keep everything straight, this is one thing. Any questions on this? It actually shows by Gaussian elimination, this procedure is really effective because, you could have a lot of equations and, it could be sort of a mess. But this is a systematic way to actually reduce things down to something that you can actually do. All right, first question. So this is a homogeneous system. So where are the pivots? The pivots are here, here, and here. What is the free variable?
X4.
Okay, good. So x4 equals t is free. Okay, so now what we do is we just back substitute up, right? So that means that 6x3 minus t is 0. So x3 is equal to t over 6. Are you okay with that? And then we back substitute up again. So we have 2x2 minus x4, which is t, is 0. So then I get that x2 is equal to t over 2. Okay? And then finally, this is very nice because there's only like, you don't have to add or do all this other stuff. So 3x1 minus t is equal to 0. Yeah. And so that means that x1, what is x1 going to be equal to? T over 3.
T over 3.
Okay, so now I can write the solution out. And it's x1, x2, x3, x4. And you're going to only have the homogeneous part, obviously, the t, right? And x1 is going to be equal to what, 1/3. And x2 part is 1/2. x3 is 1/6. And x4 is 1. Okay, so this is the general solution for this system of equations. But I asked before that the solutions be integers. So what we want to do is we're going to look at the smallest number of atoms. So now let's consider the smallest number of atoms. To balance the equation. Okay, so can anyone tell me what we should do to get the smallest number of atoms?
Multiply, scale everything by 6.
Right. Now we want to use t equals 6. Okay, so then we have a solution. x1, x2, x3, x4. When we multiply by 6, I get what? I get 2, 3, 1, 6. Okay, so this is the smallest number of atoms needed to balance the equation. All right, any questions on this? So let me just kind of briefly recap. So the idea is that you start out with 2 compounds. So it's like sodium phosphate, beryllium nitrate, and then you put them together, you get this other compound, beryllium phosphate plus sodium nitrate. Now, what you want to do is you want to balance the equation. So you just stick x1 times the first compound plus x2 times the second compound. You got more compounds, obviously. And that has to equal to x3 times the compound that you get plus x4 times the other part of the compound that you get. And then you just count the number of atoms and you equate both sides. And you just be careful by making sure that you order things very neatly. So once you order things really neatly, you can set things up so that you get a system of equations, homogeneous system of equations. Once you have a homogeneous system of equations, you just turn the crank. Use Gaussian elimination, be persistent, row reduce, row reduce, row reduce, row reduce. Finally get to the end. You solve the homogeneous system. And once you have the homogeneous system, in order to get the minimum number of atoms, you may have to multiply by a certain number to make everything a whole number. Okay, and that's basically it. Okay, you'll have a chance to do this on your own. Okay. All right, so questions? Questions from the outside?
I have a question
Sure.
real quick, just about Let's say you have a matrix that is not augmented.
That's not augmented. So you may have to like put it in augmented form.
Right. Can you row reduce something that is not augmented?
Yeah, that's kind of what we did, right? I mean, right now, this is augmented, right? This starting point. So I guess, I'm not sure what you mean by augmented, maybe that's,
I mean, like it, like it equals something, I suppose. So like in this case, everything equaled 0, which made it a homogeneous solution.
right.
However, if they ask you to row reduce where it's just a generalized notion, so your like right-hand column is like B1, B2, B3, B4, B5.
Right.
How would do you just row reduce with the B's?
Yes, yeah, exactly. When we did that, this was sort of what we did in the first problem, right? This is exactly what we did in the first problem. We row reduced here, we had B's, and then we have to, when we row reduce, we have to actually row reduce the B's too.
Okay.
So we did this in this situation.
All right. Thank you for the clarification.
Okay, good. Other questions?
I also have another question if I can ask that real quick.
Yes?
When you substitute in the free variable like t, where you get like, for instance, like 6x or 6x to the 6x3 minus t equals 0, where do you get that equation from?
Oh.
Like I'm
yeah,
just
so
confused on where you're getting that from.
Yeah, I'm just getting, so I'm starting down here, right? So this is where this is where I'm getting it from. Because
Okay. All right.
This one corresponds to x1. This corresponds to x2. This corresponds to x3.
Okay. All right. Okay, that makes sense.
So when
Thank
you
you.
back substitute, you're basically using a system of equations which is easier to handle than your original one. That's the whole idea, right? You do this nice form so that you can just kind of run your way out. Okay. Other questions? Great. Okay, so we will see you on Friday.
Thank you.
Thank you.
Okay.
Thank you, Professor.
Thank you.
I'm not able to see these recordings on Kaltura.
Yeah, this is why I want to get rid of this. I want to like put them on like a YouTube channel so we don't have to deal with this anymore. So it's been a problem. I mean, I'm sorry about that.
Okay. Do you know when we'll be able to like review the lectures?
I hope by this weekend.
Okay. Thank you.
I downloaded all the videos so far, not including this one. So they're on my computer. They're ready to be uploaded. So as soon as my daughter teaches me how to make this YouTube channel, we should be good to go. Okay?
Okay. That sounds good. Thank you.
Thanks.
Have a great day.
You too. Okay, bye-bye. Yes? So, shut this down.